So the execution of the memory commands, such as these instructions as the sequence: read display, clear display, increment display. What we're going to read is read into the accumulator, and display, the DIS will take the accumulator, and then read again into the accumulator and display again, and clear the accumulator and display it, increment the accumulator, display it. Add is to add what the accumulator has currently plus the user input, the 4-bit input, and then display is to have the DIS register copy from accumulator. And we do complement, meaning what's in the accumulator will be inverted, and then we're going to display that, and then increment again to increment the accumulator, display that, and rotate the left and display what's in the accumulator. So you can see once the program loads, it's running by itself with a 2-second clock cycle. So you can see that blinking takes 2 seconds, 1 second on, 1 second off. That's 1 second. That's one cycle, one clock cycle. And every time there's a CPU instruction, it takes 3 cycles to fetch and execute. First cycle we fetch it. Second cycle we decode, execute it. The third cycle we increment the program counter and maybe display as well if the command happens to be display decimal 7. Okay, so here's the reset button. Once we reset it, the user input can be served right here during the runtime. If the commands read, that reads from here. So we reset this, and then the user input is 1. It blinks 3 times to fetch the instruction execute, which is read into the ACC, and then it's going to blink 3 times, which is to fetch execute the display. So that's why the display shows now as 0001 according to the input. So that is the 2 instructions being executed. First one is to read the user input into the ACC. The second one is to have DIS latch ACC. Okay, so it blinks 3 times. The control unit takes 3 clock cycles to generate the enable signals, the 4-bit enable signals in 3 different sets to do the instruction fetch, decode, and then display plus the program counter update. Okay, outcome. So let's try this again. Let's reset. And the user right now input is 1. It's going to be read into ACC, and then it's going to show as 1. Okay, and then the user input is 2, and we're going to read 3 cycles to fetch and execute read, and then 3 cycles again to execute the display, fetch and display. Okay. So then afterward the command is clear ACC and display. So it will clear ACC and then display. So it's all zeros. It's inverse logic, all zeros. And then it will do an add, meaning that it will add with do the increment. Increment. It will increment, and then you can see it displays 0001. And then it will do an add. Add will add what the input is with ACC. ACC is 1 and the input is 2, so it will show 3. Okay, that's after add. And then it will do a complement. Right now it's 0011. It will becomes 1100. Off, on. You should display off, on. And then it will do increment again. Right now it's 1100. It will becomes 1101. 1101. Okay, 1101. And then it will do a rotate left. So right now it's 1101. It will become 1011. 1011. Rotate left. and then we let it count again, it will start from the first instruction again. The first instruction is read and then display, and then that will read the number 2 in. So that's because these 16 instructions are the 16 memory locations addressed by program counter, which is 4 bits, starting from 0 to 15, and then it is back to 0 again to execute the first instruction as a fetch. So this is the diagram for the CPU to emulate, and you can see there are program counter on top, and memory on right, and instruction register under program counter, ALU under instruction register, accumulator under the ALU, and the display DIS register under the ACC. And on the left is the control unit that controls all the components in the CPU to fetch instruction from the memory and operates on what's fetched. And the control unit is the key. It takes the clock signals in and generates the EN enable signals to 4 different components, and it also reads what is coming from IR, the opcode, in order to set the EN. Now this is clocked, and EN is generated by the clock cycle, so other components can follow the EN as the clock cycle to do things, so they don't need to have separate clock cycle. And ALU is a combinational logic, so it doesn't have any memory, so what's from A and B end will be the output from Z end as the combinational logic that execute different functions like addition, subtraction, rotate, complement, etc. And memory is the one that carries the CPU instructions. We define a set of instructions as a sequence in different locations in the memory. And the program counter, when it is reset, is 0 and is used to address into the memory. And what's coming out from the memory is the instruction, or we call it opcode, or CPU command. So the instruction is going to give to up the ALU. So ALU accordingly performs the instruction. And it can take 2 operands, sometimes the instructions like addition. User input from 4 red black buttons provides the operand A, and the ACC accumulator provides the operand B, and the result coming out from the Z end of ALU is latched back into ACC accumulator. This is an old design. When registers were expensive, they used accumulator for this purpose. And the accumulator can be latched into DIS, and DIS is the one that shows on 4 dots, LED diodes. So if you don't latch into DIS, the ACC contents is not shown, not displayed. It can be further do the ALU operation repeatedly until you want to display that. So there's a display command that's a separate command from other type of ALU commands. So the control unit is the one that controls everybody by giving out enable signals. When it's given enable signal to PC, PC will upcount. To IR, IR will latch what's out from the memory is a CPU command. When it's given enable signal to ACC, accumulator will latch what's coming out from the CPU. And DIS, when it's enabled, the output LED will show the content of DIS. That's the content of ACC to be shown to tell us what has been operated upon and the results, so forth. So the control unit is the key to control everything in the right order. First, when we reset the control unit is a finite state machine back to the initial state, which is the fetch state. The fetch state is to enable the IR to latch what's coming out from the memory that has been addressed by PC. PC would reset, it will reset to 0. So the address 0 is the first instruction. And memory is kind of like a mapping of an array using the PC as the index into the array to get a memory location. And the content in that indexed array, the array element, is the CPU command, the opcode. So during the fetch state, initial state of the control unit, IR is latching what's coming out from the memory, which has been addressed by program counter at 0. Okay. And the next state, the control unit enters upon the rising clock, will be enabling the ACC to latch what's coming out from Z. And that has been the operation of ALU, taking the IR output as the opcode to operate on the operands A or B or both, depends on what kind of operation that is. And then next state, if we're going to display, we will enable the DIS to latch ACC. And the DIS are connected to the LED diodes, and the LED diodes reflects the DIS, what's in the DIS. Also, at this state, we increment PC. So program counter becomes 1 from 0, incremented by 1. Okay. If we're not going to do the display, that is, the opcode wasn't displayed, the CPU command wasn't displayed, we just do the PC increment, enable the PC. So the 4-bit enable signals generated from the control unit from clock to clock is going to be typically fetch to make IR latch, and then decode to make ACC latch, and then the third one is either both the DIS latch and the PC increment, or just the PC increment. That's the third clock cycle, and this process repeats. So you will see the 2-second cycle that has to go 3 times. That is for each CPU instruction to be fetched and executed. Very simple CPU emulation, and the pin numbers are there. We're going to have the master clock to drive a 2-second slow clock cycles, so we can observe the runtime of this CPU. And this is the top module that link all the sub modules together. And we're going to have the control units, program counter, memory, instruction register, ALU, ACC, accumulator, DIS is the display register, all linked from here. Lastly, there's a initial fast C set 0, always at pass edge of real clock. That's the master clock on board 32 MHz. We're going to fast count the fast C and assign the CLK wire to the MSB of the 26-bit fast C counter. When whenever that bit flips, it gives a 2-second cycle.